In order to explore the theoretical underpinnings of integrals, we're going to need to do a little bit of work using a notation for how to add lots and lots of stuff fairly efficiently. So we're going to be introducing a new notation, which is called sigma notation. So we are going to be using this sigma notation which has been known fondly by some of my students in the past as scary E. Okay, so this is your scary E, and what it is it's a way to efficiently write a sum of many things. So what the notation means is if we have the sum from I equals m to n of a sub I. So there's a lot of variables involved here. So essentially what it means is we're taking these terms of whatever we are working with and we are adding them up. And how we define these terms depends on the sum that we are trying to do. So sum from I equals m through n of a sub I is equal to a sub m, and the subscripts are just a notational way that we can organize these. So we're just organizing what we're adding. It's a sub m, which is the a that we're starting with, plus the next a after that, plus the next a after that, plus ... until we get to the a before the one that we end with, and then the a that we end with. So it's taking from one number to another and adding them all up. Okay, so another way we could think about this, we can use it to add up results or y values of a function. So we can think of I equals m to n. This is our index, which we're counting using counting numbers from m to n of f of I. So this would be like f of m plus f of m plus 1 plus ... plus f of n minus 1 plus f of n. And we call I is the index of summation. And it takes on integer values from m to n. So if you want fractions or things like that involved, you're going to have to set up those fractions and how you define your AIs. So let's look at a few simple examples of how we can set up a summation. So let's say we want to add the sum of the first three square numbers. So this would say, we would say I is equal 1 to 3, I squared. So we're going to do, what that is telling us to do is that we are going to add up 1 squared. That's our first number. Next integer in order is 2, so plus 2 squared. Next integer in order is 3 squared, and because that is our n, that's the number on the top, we stop there. So this is equal to 1 plus 4 plus 9, which equals 14. Okay. We don't necessarily have to use I to represent our index of summation. We can use j if we wanted to. That's okay. Let's say we wanted to add up from j equals 3 to 5 of 3 to the power of j. So that would mean we're going to take 3 to our first power is 3, so 3 to the third, plus 3, because we haven't changed the 3. J is what's changing. Next number after 3 is 4. Plus 3, next number after 3 is 5, and since that's our final number, we stop there. Okay, so it's where you are starting. So 3 to the third plus 3 to the fourth plus 3 to the fifth in your head is 351. I actually don't care if you do it in your head. So C, let's say we want to do the sum, k equals 3 to 6 of 1 over k. So we are going to do 1 over, our first k is 3, plus the next k is 4, plus the next k is 5, plus the next k is 6, When we add those all up and find a lovely common denominator, if you want 3, 4, and 5, that's 12 times 5 is 60. You need a common denominator of 60. That winds up being 57 over 60 when you find that lovely common denominator. And D, if I want to sum I equals 1 to 5, 3. Well, I don't have a place to stick in my I, so the first one is 3 when I equals 1, plus the second one when I equals 2 is also 3, plus with when I equals 3, plus when I equals 4, plus when I equals 5. So that is just 15. So if you're summing a constant over I, you're just going to add the constant that many times. So essentially that is a really fancy way of writing 5 times 3. Okay, if you want to confuse a brother or sister who may be in like grade 3, that would be a good way to do it. Example 2. So now what we're going to do is we are going to rewrite this. So we're going to write the sum 3 squared plus 4 cubed plus 5 to the 4th plus dot 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 plus 10 to the 9th using sigma notation. Well, there's often a really large number of ways that we can write something using sigma notation. So I'm going to show you 3 possible ways, and then if you can think of another one, that would be fantastic. Okay, so I notice we're starting at 3. So let's say I want to see where I'm starting. So if I want to use I as being the base of my exponential expression, so I'm going to let I go from 3 to 10 because that's what my bases go to. So that means my base is going to be I. The exponent is 1 less than the base, which would make my exponent I minus 1. So it's I to the power of I minus 1. Or let's say I wanted to make the index of summation start at, let's say, j equals 2. So I'm going to make the exponent my j. So my exponent is going to be my j. The highest exponent is 9. So j is going to be 2 to 9, but I'm going to be raising j plus 1 because I want to start with 3 and end with 10 to the power of j. Or it could be 1 plus j, up to you. Or let's say I really wanted to make this challenging for myself and I said, well, I want to start at 1. So let's make k equal 1. Well then, my first one is 1 plus 2. My second one would be 2 plus 2. My third would be 3 plus 2. So I'm going to be taking k plus 2, and I'm going to be raising it to the power, well, 1 plus 1 is 2, 2 plus 1 is 3, 3 plus 1 is 4, and we're raising it to the power of k plus 1. Okay, and in this case, so if I'm raising k plus 2 to the power of k plus 1, the last number I'm going to hit is going to be 8. And there are an infinite number of possible ways you can write it by changing j plus 1, k minus 1, however you want to organize it. Okay, so there are some useful rules surrounding sigma notation that are going to help you simplify what we need to do, and I'm also going to give you some useful sums. Okay, so rule number 1, the sum from I equals m to n of a constant times ai, okay, where c is a constant, is the same as the constant times the sum. And this is just an extension application of the distributive property. So if you're multiplying each term in a sequence of sums by c, then you can multiply the whole sum by c instead of multiplying each term by c, sort of like factoring out a c. If I'm summing from I equals m through n, a sub I plus b sub I. So I'm summing a sum. I can sum each separately and then add my result, which can be really useful. And this is a consequence of the commutative property of addition, which is that we can rearrange the order of addition as much as we would like. Okay. And property 3 combines the two because we can think of subtraction as just multiplication by -1 in combination with addition, which says that if I have AI minus BI, that's the same as the sum from I equals 1 to n. Sorry, I equals m to n of AI minus the sum I equals m to n of BI. So if you're adding or subtracting, you can separate out the sums and do it as two separate sums. If you have two separate sums, you can do the sum or subtraction first and then add them up. We also have some useful sums that are going to help us write it in what we call a closed form. Because sometimes, and this is going to be what sort of gives us the springboard to be able to move to defining an integral using sums. Okay, so first useful sum. The sum I equals 1 to n of 1 is n. So if we're just adding 1n times, we get n. Fairly straightforward. Number 2, the sum from I equals 1 to n of any constant, we saw it with 3, is equal to n times c. Okay, where c is a constant again. Number 3, the sum from I equals 1 to n of I, if we're just adding up the first n numbers, is equal to n times n plus 1 divided by 2. And if you got a chance to do arithmetic sequences, this is related. Number 4, the sum from I equals 1 to n of I squared equals n times n plus 1 times 2n plus 1 over 6. And we call this closed form with it where it's written in terms of n. If we are writing it as a big sum, we call it open form. So this is like 1 squared plus 2 squared plus ... plus n squared. So this would be open form. If you're asked to write something in closed form, it means we want it with the n that is n not with an index of summation and not as a sum. And our last possible useful one is the sum I equals 1. Not that there aren't any other useful sums. Calculus 2 in college, you will get some beautiful sequences and series, and they love using this sigma notation. So n times n plus 1 all over 2, the quantity squared. Okay, and that is the sum I equals 1 to n of I cubed. Let's prove number 3. Okay, we're not going to prove all of these, but it's nice to see a proof of number 3. This one's kind of a fun one. So if we have I, the sum I equals 1 to n of I, okay, this is equal to 1 plus 2 plus ... plus n minus 1 plus n. I'm going to write it a different way now. Sum of I equals 1 to n of I is n plus n minus 1 plus ... plus 2 plus 1. And I'm going to add these together. So if I'm adding a sum, the sum plus the sum is equal to the sum of I plus I, which is equal the sum of 2I, which is equal to 2 the sum I equals 1 to n of I. Also, just by definition, you add something to itself, you get 2 of that something, even if it's a complicated sigma notation expression. Here, I'm going to add vertically. N plus 1 is n plus 1. 2 plus n minus 1 is also n plus 1. If I had written here a 3 and n minus 2, I add them together and I get, well, lo and behold, n plus 1. And if I continue, I will always continue getting n plus 1. So n minus 1 plus 2, n plus 1. And n plus 1 is also, in fact, n plus 1. So I have gotten n plus 1. And because each of my lists contained exactly n numbers, I have gotten n plus 1 n times. So if I am adding up something, a certain number of times, that is the same as multiplying by that number. So 2 times the sum I equals 1 to n of I is equal to n times n plus 1. n plus 1 added up n times. But now I have a 2 over there. I can divide the right-hand side by 2, so I get the sign of I equals 1 to n of I is equal to n times n plus 1 over 2. So this is an example of just a classic deductive proof where we are simply starting with stuff we know and we're using correct mathematics to get to something else that now we know too, because we at every step have shown why it's true and we've used correct algebra and mathematics at each step. Okay. Let's have a look at a couple more examples. So we're going to do 2 medium to easy examples and 1 of how we might utilize our special things and 1 super mega hard example. And the super mega hard example is an example that shows how we are going to be using this stuff when we get to our next lesson, which is about a special kind of sum. So example 3. Let's go medium on this one. So this is I equals 1 to 4 of x squared. Okay. Well, do you see an I? I don't see any i's, so my index isn't changing. So essentially, we are treating x squared as a constant. So if no I, or whatever the index of summation, then you treat it like a constant. So we get that this is equal to x squared times the sum from I equals 1 to 4 of 1, which is 4 times x squared, using our first handy rule. Or you can just think of this as x squared plus x squared plus x squared plus x squared, which is 4x squared. Because again, there's no I, so nothing's changing. You're just adding the same thing 4 times. Okay, let's look at an example that maybe is a little bit more challenging. So let's say I want to do the sum from k equals 1 to 10 of k times k plus 1. Okay, so the first thing I'm going to do is I'm going to expand the brackets here because I don't have any rules for products of sum, but I do have a rule for a sum of sums. So that gives me k squared plus k. So we're summing that. And now that's still going to be 10 terms. I would really very much prefer not to have to write this out. So let's simplify this further. So we get k, this is the sum k equals 1 to 10, k squared, plus the sum k equals 1 to 10 of k. Now I have a handy-dandy useful sum in terms of n, where I can write it in closed form for both k squared and k. So I'm going to actually use these. So this is equal to n times n plus 1 times 2n plus 1 all over 6 plus n times n plus 1 over 2. And those are my for k squared and for k. So now I can just plug in n, and I get 10 times 10 plus 1 times 2 times 10 plus 1 all over 6 plus 10 times 10 plus 1 over 2. And that gives me 385 plus 55, which is 440. So that's a lot easier than actually just trying to add all of that stuff up, which you could do, but it would take you a really long time. Okay, so I know you would be super disappointed if I actually didn't do a mega hard example as promised. So here is our mega super extra hard example. So we are going to look at the limit as n approaches infinity. So we're adding a limit. The sum from I equals 1 to n of 3 over n. And now remember, we're going to treat n as a constant here because It's not an I. It's not the index of summation. Just n. 3 over n times I over n squared plus 1. That looks like fun, doesn't it? Let's have a go at it. Okay, so the first thing I'm going to do is I'm going to try to write everything as addition multiplication. So this is the limit. Everything that is being multiplied, write it as addition so we can simplify. So the limit as n approaches infinity, I equals 1 to n of 3 and I'm going to put some brackets here so that we can see we haven't taken our sum yet. Okay, so we've got 3i squared, we have an n squared inside and an n outside, which will give us n cubed, plus 1 times 3n, which is just 3 over n, which is just 3 over n. Okay, so there we are here. Next, we are going to split this up into two sums, and all of this is still, we are going to write the limit as n goes to infinity about 1,000,000 times before we're done, but we are going to write it at every step of the way because we haven't taken the limit yet, and it's going to be the last thing we do. I equals 1 to n of 3 I squared over n cubed plus the sum from I equals 1 to n of 3 over n. Now we are going to take anything that we can treat as a constant and we are going to factor it out of its respective sum. So we have the limit as n approaches infinity, just for housekeeping. So here 3 and n can be considered as constants. So we're going to factor a 3n cubed sum I equals 1 to n of I squared. Ooh, that looks like something we have a shortcut for. Plus 3 over n is actually just a constant again because there's no I in it. If there's no I in it, no index of summation, we can treat it as a constant. So we can just pull out the 3 over n, and this is the sum from I equals 1 to n of 1. All right. So now we can take our sums because we have some super handy dandy sums, and then we're going to get to cancel some stuff. So this is the limit as n goes to infinity. We're going to get rid of our summation signs. How exciting. So we have 3n cubed. Sum of I equals 1 to n of I squared is n times n plus 1 times 2 n plus 1 all over 6. I would be memorizing that. Plus 3 over n times n, because the sum from I equals 1 to n of 1 is just n, and a closed bracket. So now what can we cancel? Well, we can cancel that n, make that a squared. That's nice. We can cancel that 3, make it a 1, and that 6, make it a 2. That's also nice. Not much else we can do. Here we have an n and an n cancel, so we just have a 3. So this is the limit as n approaches infinity of 2n squared plus 3n plus 1 all over 2n squared. And then we are going to do plus 3. And now we can take our limit, and we can take the limit of the different parts of the sum separately, so we can divide everything by n squared. If we go through and divide this bit by n squared over n squared, so we get over n squared over n squared over n squared over n squared, and this goes to 0, and this goes to 0, and these cancel, leaving us with 2 over 2 as we take our limit, which gives us 1. So this is equal to 1, and then the limit as n approaches infinity of 3 remains 3. So it's 1 plus 3, which is 4. And now just to appreciate the scope of this problem, let's just take a minute. Just take a minute and look at the whole thing. We started with the limit as n approaches infinity, the sum from I equals 1 to n of 3 over n brackets I over n squared plus 1, and we got 4. Amazing.